One of the biggest challenges we face in London is how we deal with the issue of water scarcity with a growing population, yet at the same time ensuring it is done with a maximum energy efficiency and ensures sustainable development. Our project is to design a water treatment facility utilizing water from the Hampstead and Highgate ponds. Our aim is to provide clean drinking water from a sustainable source, adding value to the local economy and community. We will treat 1 megalitres of water per day, which will provide clean water to over 6,500 people. We have adopted a holistic approach to carry out the design project in order to achieve a continuous optimization of the design ideas throughout the project. Careful planning and management roles have been defined to ensure the delivery of the final project is met and on time. Throughout the design process, we have ensured that every decision made takes into 4 key criteria: ensuring health and safety, minimizing costs, social and environmental impact. And through each design optimization, the designs are changed to better address the key stakeholder analysis and risk mitigation strategies. In order to determine the optimal location, a multi-criteria analysis was conducted. Multiple factors were chosen based on the initial 4 design criteria and weighted according to their importance. The location 5 resulted in the most optimal solution and will be our chosen location. These are the unit processes essential for achieving safe drinking water. The water enters the system where the debris is removed through the screening, followed by rapid mixing, flocculation, sedimentation, filtration, and disinfection. At each process, multiple methods were considered and the optimum was chosen based on the key criteria.
Intake is the very first stage of the treatment process. The floating structure intakes water just below the water surface, which is the cleanest water layer. Therefore, the required treatment would be less intense. Overall, it is a safer and cheaper option. The next stage is screening, where the larger physical contaminants are removed. Considering efficiency and ease of maintenance, the first and second screens are installed in close succession at the pipe entrance. A microstrain is then placed in the plants to remove plankton and algae from the flow. Coagulation is a process where chemicals are added so that particles can stick together and form larger particles. Mechanical mixers produce a more efficient rapid mixing than hydraulic ones. For a detention time of 30 seconds, 3 mixing basins should be operating in parallel, with each basin using a radial flow turbine. Flocculation involves a slow mixing stage in order to increase the size of particles through increased interactions. Again, mechanical mixers prove to be more advantageous, especially since the energy dissipation rate can be varied independently of flow rate. A total of 9 fluctuation basins should be provided, operating in 3 parallel streams. There are 3 basic geometry design, and we picked the rectangular shape after a thorough research. To improve the performance of the design, plant settlers are installed at the end of the basin, which helps increase the settling area and reduce the tank footprint. This minimizes the cost as well as social and environmental impact. In the design of filtration process, the idea is to treat the targeted water flow using minimal space requirement. We came up with a design of high-rate filter in enclosed vessels. Pressure from pumps would drive the filtration process. The system also required a backwash procedure for regular cleaning. Therefore, the whole system consists of 4 filter tanks. They are controlled by separate valves to make sure normal operation of treatment work during the backwash procedure.
During disinfection, chemicals are added to remove ineffective organisms that could potentially cause negative impacts to the public. Ozone is used prior to the addition of chlorine to ensure that small amounts of harmful byproducts are produced. Health and safety is a key consideration when designing this process because of the use of ozone. To prevent limescale buildup in pipes, we have considered adding a demineralization process to our treatment plant design. In the demineralization process, either ion exchange or membrane process can be used to reduce the hardness of water. However, the process is very expensive to operate and thus will not be possible in the preliminary design. This layout embodies our efforts to create a multi-use water treatment plant. This design is modeled to mimic a cave to add the aesthetic value of our plant. This aesthetic value could be vital if we decide to add a water treatment museum or tour in order to educate the public about the water treatment process. This layout involves excavating from the top and stacking the tanks together. Even though this plan works, it is an inefficient design. Due to the mismatch in dimensions of the various tanks, there is a lot of empty space on certain levels, while on others the arrangement is very tightly packed. In turn, this incurs costs that are necessary and many compromises on safety due to the lack of access space. This layout also involves excavating from the top, but in a wider excavation. Here, we have thought about the spacing between the tanks to allow workers to comfortably navigate the plant. You can see from this plan view that we have a minimum spacing of 1 meter between tanks and the pathways are wider still. Here in the side elevation, we show that the plan has taken into account the heights of the tanks used. Most tanks have a height lower than 3.5 meters. This allows most of them to be placed on the same platform. Only the demineralization tanks have a significantly taller height and need to be placed on a lower platform. Ultimately, this has created a significant amount of volume savings, which ultimately will be felt as cost savings. Our next steps will be to determine the capital and operating costs and conduct a cost-benefit analysis. We will look into the feasibility of multi-use infrastructures for our treatment plant, such as incorporating a hydropower generator, water treatment museum, and use of non-potable drinking water.